So today we're going to be talking about, we're going into section 3.3. It's called, I'm actually not sure what the section is called, but it should be called something like average rate of change. Average rate of change, or even better, it should be called foreshadowing the calculus. Let me shut this door. So yeah, for some reason calculus is sometimes referred to as the calculus. In any case, so this course is called, it's actually not called pre-calculus, it's called transcendental functions. But the original name was pre-calculus, and this is a course that does set you up to learn one of the greatest advances in human thought, which is calculus. Okay. So here, suppose you have a function, and the function is say, I don't know, a parabola, say x squared plus 2x minus 7. Okay, and you'd like to know where is it largest? Where is the function? Where is the function largest? Where is it smallest? Actually, let's not specify the function. You have some function and you'd like to know where it's biggest and where it's smallest. You'd like to know where it's increasing quickly, where it's decreasing quickly. This sort of thing, right? These are all questions that people kind of think about intuitively, right? When you're in a situation, you try to figure out, how can I maximize my the things that are good? How can I minimize the things that are bad, right? And you want to find out, like where is the function the biggest? Where is the function the smallest? Okay. So we'd like to be able to answer this sort of question. Unfortunately, we won't be able to do it. In this course. But once we get to calculus, then basically a whole system will be introduced to you through which you can maximize and minimize and this sort of thing. I'm wondering if I should try to give you some sense of that. But yeah, let me hold off. Let me hold on that. Okay. So right. So how do you find such points? How do you find such points? And the answer is we can't really answer this. We can't answer this yet. Except in some special cases. Okay. We can't do this except in some special cases. Yeah, actually, let me just give you. I can't stop myself, but let me just give you sort of a quick introduction to the main idea of calculus. Okay, so calculus is basically sort of like elementary school mathematics, or let me say elementary mathematics. Plus something called the limit. Okay, and the limit is this thing, sort of like the notion of infinity. Okay, so just to give you some sense of that, one thing that you would do in calculus is try to find an area under a curve. So somebody gives you this curve and says, what's the area under this curve? Okay, and really it's kind of funny, but what you do with this is you pretend that you're an elementary school student, And you say, well, I have no idea what that is, right? But a very optimistic elementary school student. So the student says, I don't know what that is, but I can tell you what I do know, okay, right? And the student says, okay, I don't know what that is, but what I'm gonna do is just approximate, okay? I know that kind of area, right? I can just see how tall it is. I can see how tall it is. That gives me some height. I know how wide it is. That gives me some width. And then I take the multiple, and that gives me the area. Okay. Okay. But the elementary school student also is very clever and says, I can do better than that. I can do better than that. I'm going to divide this thing into 2 parts, right? I'm going to divide this thing into 2 parts, and I'm going to do the same thing that I just did, right? So in this part on the right, I'm going to take some sort of big box over here, and on the left, I'm going to take some sort of covering box over here, right? So I've got, instead of my first approximation, in fact, I can do a little bit better, even though I'm just an elementary school student, and I have no idea how to answer this question. Okay, right? And then you can see what will happen next. The person will think, oh, actually, I can do better than that, right? I can do better than that. I'm going to divide this thing into 4 parts, and so on and so forth, right? So we'll get something like this: approximation, approximation, another approximation. And this approximation is a little bit better, right? And then, you take the limit of that. You take the limit of that. So you say, okay, I'm going to keep on going and see what these numbers tend to. I'm going to get different numbers, right? So I get some number, I get some big number, and then I get some slightly smaller number, and then some slightly smaller number, and so on and so forth, right? And so I'm going to get a sequence of numbers, and those numbers ought to get closer and closer to what this actually is, right? And so that's actually all calculus is. That's a lot of calculus right there. You take the unknown. So the unknown is this thing, right? The unknown is this thing, and then you say, well, that's an unknown, but here's something that is known, right? Here's something that is known. These areas, right? And then you start refining that, and you take the limit of those things, and that gives you that's actually how we get the area under such curves. Okay. So calculus basically has only one idea, and that is to examine. It is that one can determine the unknown as the limit of the known. Yeah, basically everything in calculus is this one idea. Now that sounds, like if you said that to anybody, that would kind of make sense, right? The unknown is the limit of the known. But what makes calculus unusual is that limit is something very precise, and that's what you're going to learn when you go to calculus. You'll learn this thing called limit, and see how you can combine it with your elementary knowledge. Okay. So coming back to what we're doing here, we're doing things like optimization and average rate of change. Okay. So like I said, we can't really do this except in some special cases. So at this point, all we're going to do is introduce some basic notions. So this section is just a bunch of basic concepts. Okay. So some concepts. So the first one is something called the maximum value of a function. Maximum value of a function. Okay, so you can probably guess what that is, right? So you have You have some function, it's on some domain, right? Let me draw it a little differently. Right. How would you define the maximum value? Maybe it's too obvious. Right? The maximum value is of course going to be the biggest value, right? So here's how we say that, in mathematical language. We say, f of x naught is the maximum value if f of x naught is bigger than or equal to f of x for all x in the domain. So this is the formal mathematical definition. Right. F of x naught, so f attains its maximum value at x naught, right? If that value is bigger than or equal to all other outputs that you can get. Okay, that makes sense. That's I think that's pretty intuitive, right? I'm not going to use it very often in this class, but in a calculus class, this for all turns up a lot, so much that you have an abbreviation for it, and it's an upside down A. So if you ever see this upside down A, it means for all. Okay. So in this case, you see that the maximum value is attained here, right? There's some value f of x naught, and whatever x you choose, all those values are less than it, right? So no matter what other x I take, they're less than or equal to it, right? What about something like this? So here's my function. It's on an interval AB. Does this have a maximum value? Look at the definition. According to the definition, does this have a maximum value? Yeah, it does. So there's something that's a little bit unintuitive about this. Normally, we wouldn't say that there is a maximum value. Like, I think most people would say, no, it's all the same. There's no maximum value. But yeah, in fact, in this case, because in this case, the maximum value occurs at every point, right? So at every point, you're greater than or equal to every other point. So yeah, you do have a maximum value. Okay. What about something like this? If I have something like this, is this the maximum value? No, right? Because there are other places. So x naught, you could take this x over here, and you see that f of x is bigger than f of x naught. I think f of x is definitely bigger than f of x naught. Okay. Later on, we'll make a term for this, which is called local maximum, right? It's actually, you can find there is a place where it is the biggest, right? So it's called a local maximum, but don't worry about that now. Okay. Okay, second concept, so maximum value, right? And similarly, you can define minimum value. So similarly, one defines minimum value. Okay. Next idea, increasing function. Increasing function. So again, this is an idea that I think is pretty intuitive to people, right? It's a function that goes up, right? A function that goes up. But how do you describe that mathematically? How would you describe that mathematically? Yeah, Jamie.
Positive rate of change.
Positive rate of change, but we haven't defined rate of change yet, so Don't use rate of change yet because we haven't defined it. Yeah, Olivia.
The maximum value would be infinity.
The maximum value would be infinity? Well, not necessarily. You could have a function that is just defined from here to here, say. Right? That's an increasing function, and yet its maximum value is not infinite. Right? Or you could have a function like this that gets closer and closer to some line, but so this would be an increasing function, but its maximum value is not infinity. Yeah, you said. Change in y over change in x is positive. Okay. So this is what Janie was saying. You're using the rate of change. Let me. Yes, Stella.
Maybe like as x increases, y increases.
As x increases, y increases. Yeah. So I think that's probably the easiest way to think about it. Like if you have two different x values, then the y value for the one on the right has to be bigger. Right. So yeah, that's actually how we define it. So we say f is increasing if whenever a is less than b, f of a is less than f of b. Okay, and then similarly, you can define decreasing functions. You know, whenever a is less than b, f of a is greater than f of b. Okay, maybe that's none of these are that exciting. If you're bored, that's where you should be, I'm afraid. Okay, so the last and most important idea is the average rate of change. Of a function over an interval. Okay, so you have some function f over an interval ab. And so we define that to be is defined as the difference in the y values over the difference in the x values. Okay, so pictorially, graphically, you have some function that goes like this, say, right? And what you do is you take the y values, f of a and f of b, and you subtract them, right? So you get this height, right? And then you divide by b minus a. So you get f of b minus f of a over b minus a. Okay. And sometimes I think often it's useful to think of the interval here as time, as some sort of time interval, and then that would be the rate of change over time, right? How much it's changed in over a certain length of time. Okay, so that would give you the average rate of change of the function with respect to time. Okay, but it could be something else, right? It could be, height or something, and then you get your average rate of change with respect to height, change in height or something. Okay, so you get this thing, which is often abbreviated delta f over delta x. This delta stands for change in. I'm not sure why, probably because of the word difference. Maybe it's like the difference in x, difference, and this is a D, a capital Greek D, so difference in f over the difference in x. Right, so, right, so you take this thing and you divide it by this thing. What is that? Does anybody recognize that? The change in this over the change in this, Evie?
Yes.
It's a slope, right? So it's actually the slope of, if you take a line through here, then it's actually the slope of that line. Right? So the rate of change, the delta x over delta f, is actually the slope of what's called the secant line. The secant line. So let me just give you, do some examples. So here we have f of x is x squared plus 2x minus 7. And suppose we want its change over 1 comma 3. Right. So we have some interval 1 comma 3. And we want to measure the average rate of change over this interval. And you take 1 minute and see if you can calculate it using this formula. Okay, turn to somebody nearby. Talk with them. Okay, anybody want to say what they got? Stella? Slope is 6. How did you get it? Well,
Do you want me to explain?
yes, please.
Okay, so I plugged both x values into the equation. So
Mhm.
1 squared plus 2 times 1 minus 7 equals -4.
Okay.
And then 3 squared, so 9 plus 6 minus 7 equals 8. And then I did 8 minus -4, which is +4, over 3 minus 1 equals 4 over 2 equals 6.
Right, so you got 8 minus 4 over 3 minus 1, so you get 12 over 2, that's 6. Right. So you just plug these. Everybody okay with that? Right, and again, if we were thinking of this as often, in physics, you think of this as a position. You think of this as the position of a car, say, like you have this car on a linear track. Let me draw the track this way. So you have a car on a linear track, right? And at time one, it's at -4. At time 2, it's at 8, right? So it starts here, and then it gets up to there in 2 seconds. You know, if this is measured in seconds, in 2 seconds, it's traveled from -4 to 8, and so its speed, right? Its speed is the change in position over the change in time, right? Change in position over change in time. So you get the speed. So that'd be 12 units of length over 2 seconds. Right? So 6. This would be 6. You know, whatever, 6 inches, say, per second. Right? The average rate of change. What will happen a lot is that we actually don't want to get it over some specific interval, but we want to get it over a general interval. So, like, we want to get it between A and B. So we have some function. I don't know what it looks like. I mean, this is some sort of parabola. You have some function, and we want to get its change over some interval A and B. And so you need to be able to do this thing a bit more abstractly, right? So if I ask for the rate of change, same function. So f of x is x squared plus 2x minus 7, and I say, what's the rate of change? What's the average rate of change over A comma B? Okay. How does that rate of change depend on the endpoints? Take 1 minute and see if you can write down something for that. Okay, turn to somebody nearby, talk with them. Okay, anybody want to say their answer to this one? Or just start us off? We want to get f of b minus f of a, right? Here's the definition of rate of change, right? So what's f of b? Thank you, yes?
B squared plus 2b minus 7.
we take that, and we subtract off a squared plus 2a minus 7. And we divide that whole thing by b minus a, right? So we get, I'm going to put things together in kind of a funny way. We get b squared minus a squared plus 2b minus 2a, and we get minus 7 minus, okay, oops, that should be me. I saw Stella's eyes widen. Okay. Can anybody make this a little simpler? Got b squared minus a squared. You recognize b squared on minus a squared. That's the difference of squares thing, right? So let's replace that with b minus a times b plus a. Okay. So, and then you see you can do some cancellation, right? So let me bring this up here. We have, I'm going to split this into two fractions, right? We've got, so I'm going to have the first part and the second part. To b minus a over b minus a. Right? And you see what I can do. What can I do? Take 10 seconds and write down the cancellation that occurs, or what happens. Just to make sure that you guys know what you're doing. Okay, so you see what happens, right? We have a factor on the top and we have a factor on the bottom, so we can get rid of this. We can get rid of those factors. Right? Similarly, we have a factor on the top, we have a factor on the bottom, and so this thing turns into b plus a, and that turns into 2. Okay, so that turns out to be the average rate of change. Right, the average rate of change over an interval is the sum of the endpoints plus 2. Okay. That's kind of cool, right? For this parabola, right? We have some sort of parabola, right? And we can, if we want to get the average rate of change between 2 and 7, that's, I don't know what that is. Between 2 and 7, we know it's going to be 11. Okay. So you can get a general formula. This is going to seem kind of strange, but later on, when you do calculus, you're also going to want to be able to do this thing. You express the interval a little bit differently. So instead of calling it a and b, so a and b focuses on the coordinates of the endpoints, right? But you could also write this as like left endpoint and left endpoint plus the length. Okay, so yeah, so maybe I'll no, I'm going to leave it like this because this is often how one writes it. Okay, so instead of expressing it in terms of the endpoints, you say left endpoint and length. Okay, this sort of emphasizes the left endpoint. Why? It's just like the equations of lines, right? Sometimes you change the equation of the line because you want to emphasize a different aspect of it, right? In this case, we're going to emphasize the left endpoint and the length of the interval. Okay. Okay. So, if we wanted to make a formula for this, for the average rate of change over this, so it's a different form of interval. Well, we do the same thing, right? So have f of x plus h minus f of x over what? X plus h minus x, which is just h, right? Which makes sense, right? Because this b minus a is the length of the interval, right? B minus a is the length of the interval we're dividing by the length of the interval, which is h. Okay. So it's slightly simpler to start off this way. Okay. So we do the same sort of thing, right? X, we would get, well, take 10 seconds and write down what this expression expands into, please. Same with the same function. Okay, what do you get? What's f of x plus h?
X squared plus 2hx plus h squared plus 2x plus 2h minus 7.
Okay. Is that everybody okay with that? Right, you took the x plus h, you squared it, and then you subtracted, you added on twice of that thing, and then you subtract 7. Right. And then we want to subtract off. We're going to subtract off x squared plus 2x minus 7, and then divide the whole thing by h. Okay. And you see what happens, right? The x squareds are going to cancel off. The 2x's are going to cancel off, right? So we'll get 2xh plus h squared plus 2h, right? The x squareds cancel, the x's cancel, the minus 7's cancel, and we're left with 2xh plus h squared plus 2h, quantity over h. Okay. Right. And then you can, what do we do next? Divide by h, right? You can factor an h out of the top, right? You get 2x plus h plus 2 quantity times h over h, right? You can distribute an h out of the top. That gives you this h as a factor, and so you can cancel it, and you get 2x plus h plus 2. So that's the average rate of change over an interval whose left endpoint is x and whose length is h. Okay. Is that okay for everybody? I mean, so basically all we've done is said, okay, we have this idea of average rate of change. We calculated in one concrete case, and then we calculated in two sort of more abstract versions, right? Where the first case was, in terms of the endpoints, and the second one was in terms of the left endpoint and the length. Okay. Yeah. The reason one cares about this sort of thing is because of the following sort of problem. So you don't have to know this. This is just for your education. Okay. So if you want the slope, right? If you want the slope between 2 points A and B, or say x and x plus h, it's pretty straightforward to do. Right? You just take those two values and then divide by the length of the interval. Right? That's the average rate of change. But the complicated question that mathematicians wanted to know was, so this was like the speed of this car. Right? This car backed up and then it went forward. Right? And you get the average speed of the car over this time interval. Okay. But what mathematicians wanted to know was, how do you talk about the speed right at that point in time? Right? The speed right at that point in time. Right? The speed right at that point in time should be the slope of a line that just passes through that one point. Right? That's called the tangent line. So it's easy to get slopes of secant lines. It's hard to get the slope of the tangent line because you only have one point, right? You can get a slope with 2 points. Everybody can do that. But how can you get a slope with 1 point? Okay, so this was a really strange, difficult question for people in the 17th century. Okay, right, how do you get the slope of the tangent line through that point? It's like when you're driving, like how do you know your velocity at that one point in time, right? It's easy to figure out your velocity over you calculate how far you've traveled, over how long you've traveled, how much time you took. But how do you figure out your instantaneous velocity? Okay, and so this is again this problem is solved with calculus, and you say, well, I don't know how to do that. Okay, I don't know how to do that. Again, you revert to intelligent but persistent child mode. Okay, you say, I don't know how to do that, but I do know how to get these slopes, right? I do know how to get these slopes, and well, I do know how to take that slope, and I do know how to take this slope, and I do know how to take this slope, and I do know how to take this slope, and so on and so forth. And so what you do is you let the interval become infinitely short. Okay, you let the interval become infinitely short. You let this h tend towards 0, and see what number you get there. Okay, so and as you see, we've got the formula for it, right? The slope of this line is actually 2x plus h plus 2, right? So if you let h go to 0, what's going to happen to the slopes? Your left endpoint is x. Let's say that x was 1. Okay. Right? Well, what's going to happen? You get 2 plus h plus 2, that's 4 plus h, and then as h goes to 0, it's going to be a slope of 4. Right? So this is again the idea of calculus, the strange power of calculus, that you have these problems that you don't understand, and you approach them by taking the limit of problems that you do, simple problems that you do understand. Okay. So yeah, that's what you'll do, and that turns out to be like revolutionary in the 17th century. It's like the beginning of the science of physics and stuff. Okay, we're gonna stop there.
Before class, I checked there wasn't a place to see the homework.
I'm sorry. I think I've opened it now. So you have until 11 o'clock, not midnight, 11 o'clock tonight to submit the homework.